All right, we're going to look at how energy works in a spring and how energy works in a pendulum. Basically, how energy works for these simple harmonic motion problems. I'm not going to spend a ton of time on this because we've already talked about energy. We're just going to take everything that we've done with energy before, where we have mechanical energy turning into kinetic energy, when we have potential energy turning into kinetic energy, and apply it specifically to these situations and see what kind of extra information we can get out of it. So, let's look first at a horizontal spring. That's just moving side to side, so we don't have to deal with gravity. So, we have our x0 position, which is our equilibrium position, and then we have our amplitudes, x equals a and x equals a. At equilibrium, the spring is not stretched, so there's no spring potential energy. But at x equals a and x equals a, we have our maximum potential energies. So let's look at a couple other things that we have. Maximum potential energy is at x equals a and x equals negative a. Since it's a spring, the potential energy is 1/2 kx squared. So our maximum potential energy is going to be 1/2 ka squared. Now, because there's no kinetic energy at the amplitude, because we've stopped and are coming back, the total energy at x equals a is also potential energy, 1/2 ka squared. So that's my total energy for the problem, 1/2 ka squared. And we know that total energy never, ever, ever changes. That's good. So my total energy is 1/2 ka squared. My maximum kinetic energy occurs when we don't have any more potential energy. And that only happens when the spring is not stretched, which happens to be the equilibrium position. So my max kinetic energy is at x equals 0. And I know that my max kinetic energy will always be at equilibrium. Any type of simple harmonic oscillator that we have, maximum kinetic energy is always at equilibrium. Now, because of the conservation of energy, all that potential energy we had is turning into kinetic energy. So, the maximum kinetic energy is equal to the total energy. We already know the total energy. So 1/2 mv squared for kinetic energy is equal to 1/2 ka squared. And from that, we could find the maximum velocity of this object. Now, some things to remember. Remember that the spring constant, we can always find that if we have the period. We can always find that from the period for a spring equals m over k. And we'll do an example of that at the end. This is what we do with a horizontal spring. Oh, and just to show you the algebra, we're going to solve that for kinetic energy. For the spring constant. So we divide both sides by 2 pi, and then we square both sides. So it's t over 2 pi becomes t squared over 4 pi squared equals just m over k. Now we have to do some cross multiplication, get k on top. So k is equal to 4 pi squared m over t squared. That's how we can get the spring constant if we know the period. Just a good piece to know. Now, energy in a vertical spring is a little bit more fun because we're adding gravity in. So there are 3 lengths we're concerned with. One is the unstretched length of the spring. One is the equilibrium position of the spring with the mass in it. So imagine we have just a spring hanging and then we add a mass. If we let that gently fall into where it stops moving, that's going to be this equilibrium position. And then we have the bottom position. So if we add the mass to the unstretched spring and drop it, it's going to fall all the way down, stretch out the spring, and pop back up. That's this last position that we're drawing. That's kind of at the bottom of our motion. Let's go ahead and label these. First one is unstretched. The second one is equilibrium. And the third one is the maximum stretch of our spring. So we'll draw that blue line for equilibrium, call it x0. That top one is going to be one of our amplitudes, and that bottom one is going to be our other amplitude. So we're looking at this as if we drop a mass from that unstretched spring. And we're going to pull it through equilibrium down to that bottom amplitude. Now, one thing that we can do, given the spring constant of the spring, is find the equilibrium. So we're going to do one. So that equilibrium position is where the net force is equal to 0. That's where we're going to have the gravity pulling against the spring force, and it's where those two things are equal to each other. So we can find the stretch to equilibrium by just doing mg over k. And in this situation, I'll show you where those are in a second. Now, at the lowest point is where we have all of that gravitational potential energy and turning it into spring potential energy. So we get all the energy from the top, which is gravitational potential, and it's not moving. And that bottom spot where it turns around and comes back, we set those two equal to each other. So we have gravitational potential energy equal to the stretch of the spring, or the spring potential energy. And so by solving these two equations, you can find the amplitude and that lowest point. So x for equilibrium, to give me the amplitude that we got in number 1, is the distance from A to that x0 position. And the height that we used in the second part goes from the top to the bottom. And the next thing that we can do for max speed is the exact same thing that we did above, and say that the 1/2 mv squared still equals 1/2 ka squared. We can always do that for a spring. And we're going to look really quickly at an energy graph. So we have our amplitudes. Now, that first one that we just drew is the kinetic energy. When we're at the amplitudes, we're not moving. And when we're at x equals 0, we're moving very fast. So we start off with 0 kinetic energy, it gets higher, and then it gets lower again as we move between the amplitudes. The potential energy is the opposite of that. Out at an amplitude, I have maximum potential energy because I have maximum stretch. When I'm at the equilibrium position, that's the unstretched length, I have no more spring potential. And then the total energy is the black line on the top. The total energy is always the same. That's the conservation of energy. All right. The next thing we're going to look at is energy in a pendulum. We played with pendulums in class. So there's my pendulum. We're going to raise it up to a length. Energy in a pendulum is really easy. Let's look at spot 1 and spot 2. At spot 1, we have our maximum displacement from equilibrium. Which means at spot number 1, our velocity is 0. We have maximum acceleration. And we have total energy equal to potential energy. And at this point, that's gravitational potential energy, mgh, where h is that height right there. How much higher point 1 is from point 2. At point 2 is equilibrium. Our forces are balanced at that point. And at equilibrium, we have a maximum velocity, 0 acceleration, and all of my energy is kinetic, or 1/2 mv squared. And I could figure out